Hello, everyone. Welcome to pre-lecture 4. This is going to cover heating curves and phase diagrams for our lecture on Thursday, September 9th. Okay, so if we start with heating and cooling curves, just depending on which direction you go. If you remember from General Chemistry 1, we had a unit on thermochemistry talking about heat, which we use the variable Q to represent. And how it relates to changes in temperature. So typically, if we want to measure the heat of a system, we need to know the mass. It's something specific heat, that's this variable C, and then how much the temperature changes in order to understand the heat. Okay. Doesn't matter which direction you're going. This can be heated or cooled. The key thing to remember, particularly for this unit, is that the phase of matter cannot be undergoing a phase transition or a change in its state. Okay. For example, say we have a pot of water, and if we have our stove applying heat at a constant rate, then initially that heat serves to increase the water's temperature. And then it will eventually start to boil. And then at that point, we would need to change the way that we calculate for that heat. So again, this kind of Q equals MCAT, I'll call this equation. It's how we would calculate heat for something that is changing temperature. But if instead of changing temperature, we are changing phase by breaking those intermolecular bonds or forming them, I suppose, depending on which direction you're going, then we calculate Q with this equation where we have N, the number of moles of a substance, and a heat of vaporization, which is a constant particular to each substance. Okay, so heating and cooling curve looks something like this. If we were to plot it on a graph, this is a heating curve for water. So if we started at the bottom here, say we start with ice at -10 degrees Celsius, and when we change the temperature, we would calculate the total heat of the system using Q equals MCAT. Then when we get to this blue line, our ice is going to start to melt. And so while the ice is melting, it's not going to change temperature, which is our y-axis here. Instead, it will be the energy being put in as heat will be breaking those bonds, intermolecular bonds, and phase transitioning from a solid to a liquid. If we continue up our heating curve here, once all of the ice is melted into liquid, then the liquid will start to change temperature. That change in temperature will go from 0 degrees to 100 degrees Celsius. We would again use Q equals MCAT. We'll have a different C value for all of these different Q equals MCAT equations, just based on what phase of matter we're in. And we'll also have different constants for heat of vaporization, which is where we go from a liquid to a gas, and heat of fusion constant that would also be different. Okay. So this is problem number 11 from our in-class worksheet. I would suggest you try this yourself, see if you can do this. We're going to go over it in class as well, but I ask you how much heat is required to raise the temperature of 35.9 grams of water from -45 degrees Celsius to 155 degrees Celsius. And I give you all of these constants here. So if we were to start this problem, we would be assuming that our water starts as ice in its solid form at -45 degrees Celsius. And so our first step is going to be to heat that ice from -45 to 0, because that is the melting point of our ice. Step 2 would then be to melt it. Step 3 would be to heat the water from 0 degrees Celsius to 100 degrees Celsius. Step 4 is boiling the water. Step 5 is then heating the steam in its gaseous state from 100 degrees Celsius to 155 Celsius. Okay, so if we were to actually calculate that out, step 1 would look like this, where we have Q equals MCAT. Again, the mass of our system is here. The constant for ice, so this is, again, C solid is 2.09 joules per gram degree Celsius. Make sure you include your units there so that everything cancels out correctly. And so grams and Celsius would cancel out, and that leaves us with 3,380 joules of energy for step 1. Okay. Also, if we move on to step 2, we would melt the ice by using our enthalpy equation. So Q equals N, which is our number of moles. So we convert from mass to moles with molecular weight. Molecular weight for water is 18.02 grams per mole. So that would get us into moles. And then our constant for enthalpy of fusion, so this delta H fusion, when we go between a solid and a liquid, is 6.01 kilojoules per mole. If we again cancel our units, grams cancel, moles cancel, we're left in kilojoules. Something to be aware of is that when we use these different equations, one will produce answers in joules, one will produce answers in kilojoules. By the end of the problem, we will need to square that out. Okay, so we'll finish the rest in class. I would highly suggest trying this yourself to make sure you know what you're doing. So make sure you're doing that, and we'll go over this in class. Okay. In addition to heating curves, we also have phase diagrams. And so this is a succinct way to display information about different temperatures and pressures that substances will freeze, will boil, will do all of their phase transitions, as well as inhabit the different states of matter. Okay. So like I said, this combines data about pressures and temperatures for liquid gas, solid gas, phase transitions of equilibria. And so it will basically, if you find any point on the graph, it would be at a particular temperature and a particular pressure. And this phase diagram will tell you what state of matter it would exist in under those conditions. Okay. So this is what one actually looks like. Pressure will be on our y-axis, temperature on our x. And then we have these different points. So anywhere you see a line, that is representative of phase transition. Anything that is basically at the lowest temperature, higher pressure is going to be a solid. Anything at high temperature, low pressure should be a gas. And then anything between would be a liquid. Okay. We also have these special points called the triple point and the critical point, which we'll define here in just a second. Anytime you cross one of these lines is also representative of a phase transition as indicated on this diagram. Okay. All right, so like I just said, any line represents phase transition. There's also a triple point. This is the point on the graph where all three lines intersect and all three phases are in dynamic equilibrium. This actually looks really cool. This is a chemical called cyclohexane. And if you look at it, this is cyclohexane at its triple point. And so it is simultaneously freezing, boiling, subliming, depositing, melting, freezing, all at the same time. Everything is in equilibrium here. So right there, it kind of looks like it's boiling a little bit more, but then it freezes. And then it basically starts over again. Okay. So with phase diagrams, they exist for pretty much every substance. This one below is CO2, so carbon dioxide. And once you get past a certain temperature and pressure, so in this case about 100 kilopascals, you'll see that we reach something called the critical point. And so this critical point on the phase diagram would be right here. This is where a liquid and gas have intermediate properties that is something called a supercritical fluid. So it's not really a liquid, it's not really a gas, it's something in between those. And so at a certain point, we can't distinguish between those two phases of matter. That is called the critical point. And again, what you get above that point with both temperature and pressure is a supercritical fluid. Okay, this is a really great application of CO2 actually. It is how, if you ever have decaffeinated coffee or tea, it is how that is decaffeinated, is they put the coffee or tea into a pressure vessel and raise the temperature to get CO2 to be a supercritical fluid or a liquid. And then that is how they basically pull the caffeine out, which is using CO2 as a liquid or a supercritical fluid. It's also how they clean paper money. There's a great link here to a YouTube video if you'd like to see some really cool demonstrations of that. Okay. That will do it for our pre-lecture. If you have any questions, please let me know. Be happy to answer them. Otherwise, I will see you in class on Thursday and hope that you have a great rest of your day. Take care.